Hi students, in this lesson we're going to learn about chord theorems and how to use them to calculate unknown values. So the learning goals for this video, okay, after watching this video you should be able to understand the language of key parts of circle geometry and know what they refer to, and apply the first 4 chord theorems to calculate unknown values. Some things you need to recall from previous lessons: how to carry out geometric proofs, so using our symbols and our reasoning, and also the symbols used in those proofs. Alright, so a few things about circles and the different parts that make up circles. Some of these words you know already. So radius you should know, it's from the distance from the center to the circumference. The diameter goes all the way across from one side of the circle to the other through the center. A chord is just a line that goes from one side of the circle to the other. It does not have to go through the center. Right, some other parts of circles. An arc is a curved section of a circle. So this part here, for example, is an arc of a circle. We call that the minor arc, and the major arc is the one that goes all the way around and all the way around here. We call it the major arc because it's much bigger than the minor arc. So the minor arc is this small section, the major arc is the larger, bigger fraction of our circle around the outside. Now, a arc that then has radii joining it to the center, we call that a sector. So this small cut, this small piece, is called our minor sector because it's small. The leftover piece, this large piece, is called the major sector. Then in the same way, when you've got your chord going across the circle, it cuts our circle into segments. The small section is called a minor segment, the large section is called a major segment. Those are the key words and ideas and parts of circles that we're going to be referring to over the next few videos. Alright, a bit more circle terminology. An angle is subtended. Okay, key word there, subtended by an arc or chord when the lines forming the angle meet at the ends of the arc or chord. So for example, here at B, the lines creating that angle meet at A and C. So AB, BC. So we say the angle ABC is subtended at the circumference because point B is on the edge of our circle on the circumference, and it's subtended by the chord AC. And that chord AC has lines drawn to the circumference, and that's our angle ABC subtended by AC at the circumference. Angle AOB, AB is our arc here, and that arc subtends this angle at the center. So different angles, this first one at the circumference with subtended by an arc. This second angle is subtended at the center. That's where the angle is formed, at the center by the arc AB. So a couple of other things to be aware of, looking at how angles are subtended by arcs or chords. Alright, getting into our chord theorems, we have 4 we have to go through. Those will be proven on separate videos you can watch at a later date. I'm just going to go over the ideas of them here and their symbols. So we've got chords of equal length subtend equal angles at the center. So if we've got a chord here, and let's say we've got another chord here, if they're the same length, then at the center they subtend equal angles. So this angle here is equal to this angle here, if that's the center. And that's basically our symbol there. So you've got the 2 triangles with the chords of equal length, and the angles that they subtend, they are equal. Now the opposite is also true. If you've got equal angles subtended at the center, the chords, but also the arcs, they are going to be of equal length as well. So it works in reverse. The second chord theorem, chords of equal length are the same distance from the center. So if we've got this chord here, and we've got this chord here, and they're both the same length, from the center of our circle If we draw a line that's perpendicular to our chord here, that distance is going to be equal to that distance. So those chords that are the same length are the same distance from the center. And again, if we switch those statements, those clauses, the opposite is true as well. If chords are the same distance from the center, that means they're also the same length. And that's the symbol for that second chord theorem. All right, for our third chord theorem, the perpendicular from the center of a circle bisects both the chord and the angle subtended at the center. So that's how we've got our chord here, and here's our center. Let's subtend our angle there with 2 radii. If we draw a perpendicular, so a line from here that's perpendicular to our chord that passes through the center, then it bisects, or it cuts in half, our chord. So either side, those are the same, and that angle are also the same. Our perpendicular bisects our angle subtended at the center. And again, that's our symbol, with showing our clear perpendicular line and the chord being cut in half and the angles being cut in half. Again, the opposite's also true. If you've got a radius from the center of the circle all the way through, if it bisects the chord or the angle subtended by the chord, then the radius is perpendicular to our chord. Right, finally, the perpendicular of bisectors of every chord meet at the center. So if we've got a chord here, then if we've got a chord here, if we've got a perpendicular bisector that runs up this way, and a perpendicular bisector that runs down, oh, that's not very good, down this way, where they cross should be the center of the circle. Obviously not in this diagram, I haven't got a ruler, but that's the idea behind it. Perpendicular bisector, remember bisect means cut in half, perpendicular means 90 degrees. Where those perpendicular bisectors cross, that's the center of our circle. Alright, so let's do some examples using these. Alright, so we've got AB equals CD, so that means our chords are equal. And we've got OE equals 8 centimeters. Determine OF. Well, we know OF must also equal 8 centimeters because of chord theorem 2, or we can use our symbol where we've got our two chords and they're equal length, so they must be equidistant from the center. That's our second chord theorem. Chords of the same length, like A, B, and CD, we're told they're the same length. They are equidistant, the same distance from the center. Now, the second one, OM is perpendicular to AB. AB is 10. Angle AOB equals 150 degrees. Calculate AM and AOM, the angle. Now, we know that this perpendicular line bisects both our chord and our angle at the center. So AM is just going to be half of 10 meters because it's cut in half. So that'll be 5 meters, 5 meters here, 5 meters here. AM must be 5. Our angle AOM is going to be half of our angle that's subtended, so half of 150, which is 75 degrees. And our symbol for that, again, is just our triangle at the center with our radius, with our line from the center, perpendicular to our chord. That's our proof to say that the chord is cut in half and our angle has been bisected as well. Right, students, so after watching this video, you should be able to understand the key language of circle geometry, things like chords, segments, sectors, arcs, understand those words, and also apply the first 4 chord theorems to calculate unknown values.